Have you ever wondered how we can estimate distances in 3 dimensions? With 2 eyes, we have the superpower to see how far something is. How can we enable robots to do the same? The question is, can you do this with any 2 different views? What exact mathematical constraints do we need to do that? Can you and a friend together take different pictures? Can you estimate the 3-dimensional structure of the scene? Can you build a real-life 3D model just with pictures of people taking photos of different perspectives of the monument? Let's dive right in to the world of epipolar geometry and demystify the world of 3D vision through 2 eyes. First question is, why do we need this? Why do we need this 3D reconstruction of the scene? Be it self-driving cars, wherein they are driving through the scene, they need to know where they are with respect to the world. And this enables a 3D reconstruction of the scene, which is like a super fine-grained version of the Google Maps, right? Which lets the self-driving car know where it is with respect to these monuments so it can drive safely. Or maybe it's for preservation, where you want to figure out how the architecture has changed and deteriorated over time so that we can go and preserve these things. All these things require a 3-dimensional model of the world. Furthermore, enabling drones to navigate the world requires some sort of 3D reconstruction so they don't run into and bump into things. And this is called structure from motion or simultaneous localization and mapping or SLAM in robotics. And we are trying to build up to the storyline where we can reconstruct the world in 3D given a few images. And this is the first step of that puzzle. So imagine you have pictures of a monument, and these are pictures taken from different views, different perspectives, maybe different lighting, and even different weather by different people and different cameras. The question is, can we take these images as input? And these are unordered pair of images because we don't know the ordering in which they were taken. We don't know the relative alignment between these images either. Can we reconstruct a sparse 3-dimensional version of this castle in this particular case? And can we show where the cameras were with respect to this 3-dimensional reconstruction? This in computer vision is called structure from motion. In robotics, this is called simultaneous localization and mapping. In this particular case, I have also colored each of these points with the actual color of the 3D structure itself. And this can be more dense or sparser than this. So this structure, the 3D structure, is called the structure in computer vision, or it's called the map in robotics. All these little triangle-like frustums are the camera poses with respect to the 3D point cloud we are seeing. So structure from motion and SLAM are very related to each other, but they are slightly different. Structure from motion is, as we just saw, is unordered pair of images, and they could be taken from different cameras, different viewpoints, different time slices, and completely different setups. And structure from motion is a general case. It's a general problem where it could take hours or even days to run to actually get a reconstruction. On the other hand, simultaneous localization and mapping, or SLAM, is more tailored towards real-time applications on robotics. The idea is that we have a lot less compute available than structure from motion, and the images are obtained in more of an ordered fashion, which is temporally varying fashion, so we have more constraints. And we can more or less, most of the scenarios, assume that the weather has not changed significantly between these poses which were captured, which gives us more constraints to obtain information to reconstruct much faster and much more computationally cheaper and more effective way. To build up to the story of structure from motion or SLAM, we start with 2 simple images. How can we estimate things in 3-dimensional scenarios in just 2 images? It all starts with 2D correspondences, which is what are the common points in both the images, the left and right, as what we will call from now on. Note that the left and right is just a nomenclature. It's a notational significance. The cameras could be up and down as well. And this is just a notational significance, and we can call it camera 1 and camera 2 as well. So in this particular case, you will see that there are two people taking pictures of the same thing. It's the same wall, as you will see with the switchboard. And you also see that the other person taking the picture in the image of what the other person is taking. So let's pick a simple point and let's call this the correspondences. In this particular case, the correspondences were like handcrafted and manually labeled, but you will use something like a SIFT feature detector, like we have seen in one of the previous videos, to detect these automatically. If you haven't watched the SIFT video, I would urge you to go and watch that right now. So let's imagine this top left corner on this image is the x1 and the correspondence point on the second image is x2. I am going to label all the things in the left image as red and all the things in the right image as blue, so we can easily follow along where each of these points are going. And we know that we have the correspondences between them, and this can be obtained through a SIFT feature detector, or somebody has manually labeled this for us. So we will call the image on the left image, and the image on the right image. As I mentioned before, the left and right are just nomenclature significances, and they can be actually top and bottom as well. Now let's look at a cartoon representation of the same exact thing. We have basically the floor, which has two perpendicular lanes, and it's on the flat floor. And we basically have a part of a building structure. Let's imagine this is a scene from a Marvel movie where multiple of these superheroes are trying to estimate in 3 dimensions how big that building is. If the building collapses, like how much damage it would do to the things around it, and how much impact it would have. Let's assume we have like superheroes who are centered around this building, and they're trying to estimate the 3-dimensional version of this scene. Okay, so in this particular case, we have Captain Marvel and we have Iron Man looking at the scene from completely different views, and they obtain an image of their own from different views. In this particular case, as we have seen from the vanishing points, the parallel lines appear to have converged on a single point, and we see that here. And same thing from the Iron Man's image looks actually like this. Now let's denote the world point which they are like concerned with, which they are looking at this point, as capital X. All the capital letter quantities from now on will refer to the points in the word, and all the small letter quantities will refer to the points in the image. And to obtain basically where this point would be imaged on the image plane, we would take a ray from the camera center of Captain Marvel, intersect it on the image plane, and go to the world point. And we have seen this before in the previous video of the camera models, which again I would urge you to go and watch if this concept is unclear. And we will do the same thing for Iron Man to get the point on the image plane which intersects where Iron Man would see the world. Okay, so we will denote these as little x1 and little x2 just like before. And know that we have the correspondences between x1 and x2 like we talked about before, as obtained through SIFT feature matching. So the Iron Man's image looks like this, and the Captain Marvel's image looks like this. And remember, we have x1 and x2, which are the corresponding 2 points. Okay, great. So what we want to do is, we also see the ray of Iron Man pointing towards the world point in Captain Marvel's view, which is, in other words, in the Captain Marvel's image, we see Iron Man, and we see also the line which intersects Iron Man's camera center to that of the world point as imaged by Captain Marvel's image, which is little x2, right? And we saw this before as we were seeing the other person's camera and like the world point, and we could draw the line between them. And to just show that here, this is what we were seeing in the previous few minutes. Great. And we also can assume that we can join the camera centers of the Iron Man and the Captain Marvel in the real world. And this is a 3-dimensional quantity. Remember that we have the capital X, which is the world point, and we have the 2 camera centers in the world, and we can join all these 3 points to form a plane. And this plane I'm showing you here in green. This is great. And From the previous videos, we also can recall that a line in the image is this red line represents a three-dimensional plane cutting the image plane and vice versa. Remember, we talked about like the line and plane duality, wherein a line in the image represents a three-dimensional plane with respect to the camera center and vice versa. And we are going to call this line of connection of the world point, which is imaged in my current view, and which is the other camera's center in the view. And this line is going to be called as the epipolar line. So remember this word, epipolar line. This beautiful line again is important because the camera center might not be always in the image. It could be sometimes outside the image as well, but we can still draw a line from the camera center to the world point, which is being imaged on the current frame, and we can draw this line, and this represents a three-dimensional plane. It's the green plane in this particular case, and the red line is basically the one you see on the left hand side. And this epipolar line is super important because it gives us information about the three-dimensional world. You can imagine the Iron Man using a laser pointer to point at the world point, and you are taking a picture of this laser pointer, and that's the epipolar line in red. Okay, great. So let's continue doing this. And if we take the Captain Marvel's center of the image and we keep passing it through this and intersect the laser pointer of Iron Man in the real world, we will see that it all falls on the same line as we saw before. Great. Okay. So a point x1 in Iron Man's view is equivalent to an epipolar line L Iron Man in the Captain Marvel's view. Just to recap, so we basically drew a plane in the world which connects the two camera centers and the world point, and this represents a line in the other person's image. Like for example, in the Captain Marvel's image, it's the line which joins the Iron Man's camera center and the world point, and this epipolar line is equivalent to like the Iron Man pointing a laser pointer at the world, and we are taking a picture of this, right? And so every point in Iron Man's view is basically the equivalent of an epipolar line in Captain Marvel's view. Great. So this epipolar line, of course, passes through the Captain Marvel's image point x2 because it belongs to the same exact world point like we talked about. So which we can write in linear algebra as the dot product of the line and the point's homogeneous coordinates to be 0, which means that the point lies on the line. So it is x2 transpose LIM is equal to 0. So if we remember, like to match between two images, generally SIFT would do like matching or block matching through the entire image. But now we clearly see that if you have two different views which are looking at the same world point, the point can be constrained on the epipolar line of the other image. The question is, when we were trying to do matching, can we do something even more smarter? Because this was super expensive, can we use this trick in this case? The answer is an astounding yes. We can make life very simple. Instead of searching through the entire image, we can only search on the epipolar line. So if we know the epipolar line which can be computed, we can basically say, hey, it's going to lie on this line somewhere, and we are going to only go and search on this line. And we will see an example of this in the later part of the video. So stay tuned for that. So you might be wondering, okay, like in Captain Marvel's image, like Iron Man appears as an epipolar line. Is it true the other way around as well? Wherein like the Iron Man's image, does Captain Marvel appear, and is there an equivalent epipolar line which is blue in color? The answer is yes. The epipolar line does appear on the other image, other view as well, where we can flip the colors and the names, and the same thing is going to hold true again. Great. So just like before, so we have x1 transpose LCM is equal to 0. And on real images, this is what it looks like. And you can clearly here see that it passes through the camera center of the other point in the image. So, and that's why we took images like that to make it very, very clear in this particular case. Great. So now, let's change this to a different world point. And it is still true. remember that we have no assumptions about the placement of the world point. The only assumption we have made is that the world point is being seen in both of the camera views. That's the only assumption which is strong. We have made the assumption that we can basically match the features perfectly in this particular case. So the same thing happens again. Remember that all of these lines or epipolar lines have to pass through the camera center of the other one, right? And so we keep doing this. We can do this for a third point, and we can do this for a fourth point as well. So if we do this for 4 points, we can clearly see that all these 4 points match at one point or basically intersect at one point. And that point is called the epipole of the image, which represents the camera center of the other camera in my current view. And that's going to be shown as a bullseye here. These epipolar lines meet at a point called the epipole, where epipole for any line, it will lie on that line. And so this will be true. And we can do the same thing for real images as well. And you will clearly see that they all intersect at the same point. So in other words, just to recap, the epipole shows you the other camera in your image. Remember that the epipole doesn't really have to be in the finite extents of the image. It can be slightly outside as well. But nevertheless, this fact is true that it shows you the position of the other camera in the current image. So now let's make some mathematical notational assumptions. Let's call the Iron Man as the frame of reference, wherein we say that the Iron Man is located at identity rotation, so which means 0 rotation, and identity translation, which means 0 translation. And the Captain Marvel with respect to Iron Man's field of view is at rotation matrix R and translation vector T. So how can we use this to find the epipoles in the images? So we write our simple pinhole projection equation, which is lambda into the point. In this particular case, the imaging point is the epipole, and we write the standard equation on the right hand side. So this is the Iron Man's camera projection matrix, and we can do the same thing for the Captain Marvel, wherein we have the Captain Marvel's camera projection matrix. So, and these are the points we are talking about in this particular example. Okay, so let's continue with this set of equations. So now let's assume that the laser pointer we were talking about, wherein the Iron Man holding a laser pointer to the world, in the world, which is the center of the camera to the world, is going to be denoted as capital XIM. And the same thing, which is the Captain Marvel holding a blue laser pointer to the world point, is going to be called capital XCM. And the epipolar plane remains the same, is the intersection of the two camera centers and the world point. Okay. So we will have the normal vector to this epipolar as N. So the normal vector is basically the cross product between the translation vector, which is the black color line you see between the two camera centers of Iron Man and the Captain Marvel, into one of these vectors, right? And we have to take the orientation into account. So in this particular case, we are taking the laser point of the Iron Man, which is capital XIM. So the constraint essentially is that we know that the normal vector is perpendicular to XIM. So we are going to take the dot product of N with XIM, and we say that that is supposed to be 0. So now let's write this in linear algebra terms, where we know XIM is these 3 quantities, translation is these 3 quantities. So we can basically merge these two cross products and write it like this. So since we have written this as a 2x3 vector, we can split this into a skew symmetric matrix, where we can sort of write this into a bilinear. This skew symmetric matrix can be represented as T cross. It's the translation vector, and the skew symmetric matrix represents the cross product of this translation vector. So this is a trick which lets us do a lot of cool things in the future. We will use that. And also remember that like capital XIM and capital XCM are related to each other through R and T, because that's how we define the coordinate frame of reference. So we know that XIM is equal to R into XCM plus T, which is basically applying the rotation and translation to us. So here R is the orientation of Iron Man's camera in the Captain Marvel's frame of reference, and T on the other hand is the position of the Captain Marvel's camera in the Iron Man's frame of reference. So let's apply the first equation, the bilinear form, into the second equation, and this is what we have. But you'll clearly observe that the right hand side in this particular case is T cross T, which is basically like you're taking the cross product of the same two vectors, and which turns out to be 0. So the solution becomes fairly simple. So we have the Iron Man stuff on the left hand side, we have the cross product of the translation in the middle, and then we have the rotation matrix, and then we have the stuff from the Captain Marvel's frame on the right hand side. This equation is super important because it relates the laser pointer of Iron Man and the laser pointer of Captain Marvel through the translation and rotation quantities between them, which means that it somehow encodes the three-dimensional information of the scene in this one beautiful equation. And this equation is so important that it was published in Nature, which is one of the highest journals in the field, across fields of computer vision, robotics, and other fields. So this equation has a name. So the thing in the middle, the T cross R, is called the essential matrix. It is so important, it is so essential to the field of computer vision that the term is called essential matrix. So let's look at this a little more. So we can basically write E as T cross R, which is the essential matrix. And it's a skew symmetric matrix like we have seen before on the T cross part, and the R is an orthonormal matrix. So we can essentially use SVD to decouple T cross and R. So essentially, given the essential matrix, we can recover the rotation and translation. We will talk about this in the next video. But this was all fun and games, but did you notice that there was an issue with our entire analysis? So we were talking about the laser pointers in 3 dimensions. But do we really have that? We talked about this equation wherein we have the 3D position of capital X in Iron Man's coordinates and the 3D position of X in Captain Marvel's frame of reference, where E is essential matrix. But there was a fundamental issue. We do not have these 3-dimensional laser pointers, right? If we did have that, where we knew exactly where it is in the world, life was very simple. So we do not have any of these capital letter quantities. All we have is basically the 2 images, one from Captain Marvel's view, one from the Iron Man's view, which they see, and they don't really know the 3-dimensional scene structure from that. So what do we have? We have the images like we discussed, right? We have the image coordinates, which is the small letters. Can we utilize these small letter quantities to infer the capital X? That's the question we started with, right? The whole analysis was built around capital X quantities, which we do not have. But this whole storyline is not waste, because we are going to utilize the information that we know, the mapping between the small letter x and the capital letter X, through the pinhole projection equation. Okay, let's write it out for both Iron Man and Captain Marvel. And this is what it looks like. And this is fairly simple. We are going to feed this into the essential matrix equation. And we know that the capital X and from both Iron Man and Captain Marvel are given by the pinhole projection equation in the red and blue equations on the top. And we are going to feed this into this equation. Remember that we defined in our camera frame of reference depth to be positive. And if you do not remember that, I would urge you to watch the camera models video again. And we call this the depth or depth positivity or the chirality constraint, wherein we said, hey, both the depths have to be 0. So we are going to utilize those 2 facts, that these 2 are positive. So we can basically normalize it with respect to this depth value. So since we do that, now we basically have the image quantities of the Iron Man on the left hand side. Then we have a bunch of camera matrices and the essential matrix, and then we have the image quantities of Captain Marvel on the right hand side. Let's combine the K matrices and the E matrix into one quantity, and this is going to be called the fundamental matrix. So this is so important that we gave it the name fundamental matrix. So the fundamental matrix and essential matrix have a beautiful relationship between them, which is the camera intrinsic properties. And this is sort of intuitive because the world quantities and the image quantities are related through the camera projection matrix K. And that's exactly what we are seeing here. Since we're using two different cameras, the Iron Man and Captain Marvel, we will basically have the camera matrix K of both of these guys in this particular manner. Now let's look at some examples where we can understand physical intuition of movement from just looking at these things. So if I show you the epipolar lines of two frames of reference, which looks like this, remember that the epipolar lines show the intersection show the other position of the other camera. Can we hallucinate or imagine how the other camera would have moved? In this particular case, the other camera appears to be somewhere in the center, which means that the motion either was back and forth, like either going forward or backwards in time. And since it's exactly centered, it would be exactly forward or exactly backward. And if you look at it from the top view, basically Captain Marvel and Iron Man were standing right behind each other, which is the dominant motion is forward motion. What about in this particular case? This is a case where they do not intersect on the image, but if you extend it outwards, they would intersect on the left hand side. So what would the dominant motion look like? The dominant motion would be left to right, or the lateral motion. That is the dominant motion. Okay? And in this particular case, it won't be exactly sideways because it's also tilted. So either the camera could be tilting or it could be also moving forward. Remember that our entire storyline started with correspondences. So everything goes back to correspondences. The question is, if we want to estimate the fundamental matrix, how many points would we need? Which in turn begs the question, how many degrees of freedom does fundamental matrix have? So the degrees of freedom here refers to the number of free parameters, which essentially lets us tell how many point pairs would we need between Iron Man and Captain Marvel that they need to see these many points for us to be able to estimate the three-dimensional structure of the scene. The answer is fairly simple. So we know that fundamental matrix is a 3x3 matrix. So the maximum number of free parameters can be 9. But we don't know the scale because remember, we don't have capital X quantities. We only have small x quantities. So we can only get relative scale with these two views. Let me say that again. So because we do not have the capital X quantities, the two laser pointer locations between the world and the Iron Man and the world and the Captain Marvel, we only have the image correspondences. We can only estimate the rotation and translation to scale, which means that we do not have the metric unit answers here. We only have the relative things, which means that we can say something is twice as big as the other thing and twice as far as the other thing, but we do not know if that is 2 meters long or if it is 5 meters long or it's 4 inches long. Okay? And that is sort of consistent with our single view metrology case. If you did not know the height of one object, you could only guess relatively how far something is through cross ratios, and the same fact holds true even here, since we do not know the translation between the Iron Man and Captain Marvel to scale. We'll see a special case in some time wherein we can actually estimate it into metric scale. So we lose 1 for scale, and we also saw that we have this thing which is T cross R, which means that we have this to be rank 2. So we lose 1 more degree of freedom for that. So 3x3 matrix, we don't know the scale and the rank is not full rank. So we lose 2 degrees of freedom, which gives us 7 degrees of freedom for fundamental matrix. Okay. Remember that like the mapping in the fundamental matrix is image to image. So we basically do not know the scale. And rank 2 is because we know that it passes through the epipole. All the lines pass through the epipole. Okay. So what we will do practically is estimate 8 parameters and then enforce a rank 2 constraint. So let's see how we can estimate the fundamental matrix F. We will start with the equation x1 transpose f x2 is equal to 0, where these are little x's, so they are all in the image line. And we will write it out completely like this. and let's multiply it on the left and right and expand it out this way. And we see that this is a linear equation in F, which means that we can rearrange the two factors and write it in this form, wherein we have all the quantities we know on the left hand side and all the quantities which we don't know, basically as a vertical column vector. So the question is, how many unknowns does it have? So we have 9 unknowns, which is the full 3x3 matrix. But how many point correspondences do we need for this? The answer is not as trivial as you think, because each point in this particular case does not give us one equation, because the other end of the point is on the epipole. So that is not a free variable. That's a constraint we just use to remove the rank. So that means that each point only gives us one constraint. So which means that we will need 8 point correspondences. So each point pair gives us one equation because of the epipolar constraint. This is different from homography, where we were getting 2 constraints per equation per point pair. In this case, we only get 1. And remember, fundamental matrix is to scale, which means that if you scale the fundamental matrix by some random scale k, this will also hold true, and it represents the same exact epipolar geometry. So what scale do we set? It's something arbitrary. We can say that the norm of f is equal to 1, where this little f board face is the vectorized capital F, which is all the 9 elements of the matrix, and we vectorize it to be 1. Essentially, what we are doing is this. We basically solve an optimization problem this way. So what we will do is, remember we said we need 8 points. So we will basically get 8 point correspondences between Iron Man and Captain Marvel. So quickly to recap, to get the 3-dimensional structure of the scene, Iron Man and Captain Marvel have to observe 8 points which they both agree on that it's the same point. And that's each row on the giant matrix on the left hand side. And basically where the superscript shows the point number. So you have 8 of these. And we have 9 quantities in the fundamental matrix, but we enforce that the norm of that vector is 1. So we only need 8 of these numbers. So this is of the form Ax is equal to 0, which is a standard form in linear algebra. And to solve this, we will basically use SVD. So singular value decomposition. We will take the SVD of A, and we will basically say that F is the column vector of V corresponding to the least singular value. If we write this out in math, this is what it looks like. So just to recap, we basically take the SVD of this matrix A, and we basically write this as U, D, V and V transpose. And we take the last column of V, and basically that will be the one corresponding to the least singular value, and that is going to be the answer or the solution for all the elements of F. And because we know that we have to enforce this as rank 2, if you look at D, this is full rank, which means all the 3 diagonal elements are non-zeros. We know that the last one has to be 0. So what we will do is we'll forcefully set it to 0 and reconstruct it to get F of rank when we take the SVD of capital F. And this enforcing of rank 2 constraint is called SVD Cleanup. This particular algorithm, or the 8-point algorithm for estimating the fundamental matrix, which needs 8 point correspondences between Iron Man and Captain Marvel's frame of references or images, was proposed by Richard Hartley. So if you do not do SVD cleanup, what happens is the epipolar lines look like this. Since they were supposed to align on the same point, which is the camera center, and even in the other image they were supposed to align, they don't. If we squint hard enough, we can sort of see that it's somewhat an average, but it's not really perfect because it's not a literal average. And this is where, if you just take an average, the epipolar point is going to lie, right? So with SVD cleanup, the points will perfectly align at the center of the camera, and you will get the right answer. Okay, let's quickly recap and compare the essential matrix to the fundamental matrix. The essential matrix works with 2 calibrated cameras, which means that the camera matrix is perfectly known, and we know the laser pointer locations in 3 dimensions, which is why the capital X is. In the fundamental matrix, it works with any 2 arbitrary cameras, Even the camera matrix do not have to be known for this. So again, essential matrix is rank 2. The fundamental matrix is also rank 2, given that these are the equations for that. The essential matrix is 5 degrees of freedom. The fundamental matrix is 7 degrees of freedom. And the reason for the essential matrix to be 5 degrees of freedom is it's 6 degrees of freedom from rotation and translation, but you also don't know the scale, so we remove that. In the fundamental matrix case, it's 9 parameters minus scale minus the rank 2 constraint. In the essential matrix, when we do the singular value decomposition, we have 2 equal non-singular values. In the fundamental matrix, we have 2 non-zero singular values and they do not have to be equal. And you might be wondering, why am I bothered with all these fundamental matrix and essential matrix? Is it going to matter in the era of deep learning? The answer is an astounding yes, because these are basic mathematical principles which lets us make our deep learning network more explainable and understandable, and in turn adding these mathematical constraints makes our network smaller. So in this particular case, we are trying to find a dense matching between the 2 images, I and I prime, wherein for each pixel we want to say what is the corresponding matching pixels. This fundamental concept is called optical flow, and stay tuned and subscribe to this channel for a future long video on optical flow. The goal is that we are given these 2 images and we want to say for each pixel where the corresponding matching pixel is in the other image, and this is called the optical flow. So we are going to call this the optical flow vector. To visualize this optical flow, we are going to use a color map which is seen as B. The point is, we know that this has to satisfy the epipolar constraint. Take any of these 8 points and apply the 8-point algorithm and it has to satisfy the epipolar constraint. So you can do this for any 8 points, and if you do this over and over again, you will basically exhaust all the points, right? And that's what we need to be consistent. Can we use that in the loss function is the question. So the answer is yes. What we will do is we'll basically write the same exact constraint we just saw. On the top row, you see the x prime transpose into E into X, and this is the epipolar constraint. On the bottom, this is basically for the numerical stability so that we normalize this. Again, this is a work from Richard Hartley, which we just saw. So now, imagine that we have 2 eyes, we don't have a single line, right? How do we estimate 3-dimensional distances? Can the same mathematics of epipolar geometry apply? What extra special case do we have which lets us actually estimate distances to metric units? In this particular case, we have a horizontal stereo system. So we have our left and right images, eyes, and how should the epipolar lines look like? Pause the video for a second and think about it and come back. The answer is very simple. The epipolar lines are going to be more or less horizontal. What is so cool about this? That basically we have to match only on the epipolar line, which means that we only need to match in the horizontal direction, which means we can look in the same row. But life is not perfect, so it's not going to be perfectly horizontal. So how do we fix it? We can basically use the fundamental and essential matrix to warp the images in a particular way to make the lines look horizontal. This is called stereo rectification. So basically what we will do is, we will take the 2 images, we will estimate the fundamental and essential matrix, we will warp one of the images or both the images to make sure that the lines are horizontal perfectly. So once we do that, we basically can pick any point on the left image and basically only search on the same line, basically in the same row on the other image, and whichever is the minimum, that is going to be basically our matching. And instead of matching for the entire image like we have done in the past, we will only match along the same line, and that will essentially give us how far something is. And this is exactly how we can estimate distances in 3D. And since we also know the interpupillary distance or the distances between our 2 eyes, which we have learned as we have grown, and for a robot we can measure it with either a ruler or a calibration procedure, we know the exact physical distances between the 2 cameras, which essentially lets us know the 3-dimensional distances in the world through metric units. And that's the extra information we need. So for stereo rectification, initially you will have lines which are bent like this. Once we warp it, we see that they are perfectly horizontal and we can match on the horizontal lines. That gives us disparity. The disparity is like how far or how much movement there has been between the two images, which essentially encodes depth in the inverse manner. And I would urge you to watch a previous video on stereo matching to sort of make that concept clear. So we utilize this fundamental matrix based image matching in one of our research papers. What we were trying to do is stereo cameras basically have a known distance between them called the baseline, which means that as you go in depth is invalid when it's too close because you don't have any common features, and when it's too far, you also have depth, which is invalid because you don't have enough movement between the pixels. And the error in depth is basically proportional to z square, which is depth square, and it's inversely proportional to the baseline. So if we can basically grow the size or increase the size of baseline with increase in depth or vice versa, we can essentially utilize the fact that we can contain or curtail the error to a small number. And this is exactly what eagles do. Eagles have evolved with eyesight up to 8 times stronger than that of ours. They use these amazing eyes to hunt down prey the size of a rabbit from a distance of up to 4 miles away. They do that by constantly adapting their eyes such that their depth sensing range is at optimal value for tracking. So inspired by eagles, we developed a stereovision system for quadrotors which can change its baseline to adapt its depth sensing range based on the task. Such a design makes the quadrotor morphable and have an optimal depth sensing range for the required task. In this particular research work, we used 2 linear servo motors to change the baseline of our stereo camera. We show this efficacy with multiple applications. The first one is flying through a forest. The bottom bar here shows the history of baselines as a jet color map, where we going from blue to red denotes 100 millimeters to 300 millimeters in baseline. At 300 millimeters, the baseline of the cameras is actually much bigger than the robot. The robot is about 150 to 160 millimeters in size. Here we see the quadrotor navigating through a complex forest with ease of speeds of up to 5 meters per second. In this particular case, the video is stabilized and I was running behind the quadrotor to keep up, and that's how you see that glitchy movements. And the robot in this case is navigating through the forest. It's avoiding obstacles and it's going to land behind the tree on the left hand side here. And the way we made it dynamic, as you can see, like the baseline changing, is it opens up as it goes to free space and it becomes smaller when it was closer to the tree. The baseline was adjusted in proportion to the closest depth to curtail the error to be a small number. And we can also basically fly through dynamic or static gaps of unknown shape, size and location. And the same idea as before. So we have the quadrotor adjusting and finding the gap, and it basically moves and navigates through the gap. And in this particular case, we track the foreground and background regions separately. When we lose track, we redetect the gap and fly through it again. So we can fly through gaps at speeds of up to 3 meters per second with a minimum tolerance of just 4 centimeters. Again, we adjust the baseline based on the median distance to the gap to maintain. As we get closer to the gap, the baseline gets smaller, which also makes the robot smaller. And this is what our simple control policy was. So as you can see, using epipolar geometry, we can on the fly calibrate these cameras because the cameras were moving, and we can utilize simple concepts of changing the baseline to actually make the robot very robust. Just to quickly recap, can we get depth from any 2 stereo images? What is the fundamental idea to match between 2 corresponding views? What is the essential matrix? What is the fundamental matrix? What's the difference between the two? How many point correspondences do you need for fundamental matrix estimation? How can you utilize fundamental matrix in deep learning? This is one of the most fundamental concepts in structure from motion or SLAM. So I would urge you to watch this video at least a couple of times to get a very intuitive understanding of what's happening. It's fairly involved, but I have tried to break it down as much as possible. See you next time with another video. Take care. Bye-bye.